I will tell you that for this class, this week, and the week after, those classes are the most important because you will see most of the question, your midterm question from this week and 2 weeks later. Why? Because we are trying to tell you the definition in the previous classes, only definitions. But now, I am trying to ask you questions. Because you are supposed to know something, then I can request your output, like your score. We will see how much you understand from your quiz. Okay, this is how maybe I can change my material, or maybe I can reteach. I can teach you again the same material. For some part, maybe you are not clear. Okay. So for this part, as I say, it's the case for the lossy. The case for lossy electric field. Okay. And you guys know where the table is, right? And this is why we talk about the eta, wave impedance. It is the ratio between electric field and magnetic field. Actually, it's not very hard. You just divide it by 3774 if the material is air. And what happens if the material is not air? You guys know how to do that? I don't know. Let's see in the midterm, okay? Okay. In the midterm, I will give you the question more than air because we need to understand not only your electric field in the air, we also need to know the rules in different materials.
We can summarize our class. Let's summarize something we already learned. This is the electric field, and this is its corresponding magnetic field. They are together. They occur together, show up together. You cannot give me the electric field independently. If you have an electric field, you will also have a magnetic field according to your Maxwell equations. If you have E, you will have H. Together, they are together. And this field is moving in the perpendicular direction. And the reason why I write down in this form is because, like for this example, my electric field is in the direction of X, and my magnetic field is in the direction Y, and my propagating direction is positive Z, right? This is for our example. But in the real world, your electric field has 3 perpendicular independent components. We call X, Y, Z. You can have X direction of, you can have an electric field with only X direction and only Y direction and only Z direction. So you will have 3 directions of electric field. And also you have 3 directions of electric field. Okay? This is a mathematical result about what I'm talking about. If for our example, it's very easy to write down your electric field equals to the component, a function of Z and the T. Right now is our example. It's an equation of Z and the T, and in only X direction. This is our question. But in the real world, we need to write down our electric field in 3 directions. Okay. Because when we described our electric field, if we want to talk about not only T but also Z, you can write down not phasor form, you can write down like in the form of cosine, like this way. Your K is here. There is another way to describe this one in 3 directions, X, Y, Z. You can write down, you can use the vector K instead of your scalar K, and then your vector K equals to this part multiply your unit vector X. For this equation, you have this part multiply X, right? And then you can pick up only your this part multiply X. You redefine this one like part of a vector of K. Okay? And the total K will become Kx, Ky, Kz. In 3 directions, they are 3 different K. If my wave has more than 1 direction, like more than X, I have Y and Z. So you can redefine your K. You can put your vector, unit vector, in there. Okay? So your vector K, you can rewrite your unit K equals to some unique vector N. N is not just only X, Y, Z. It is a combination of X, Y, Z. And then multiply a new K0. You redefine everything with a new vector, and N is the new direction, which is not only X or Y only, it's a combination of X, Y, Z. Okay? And then you also, your Z, you can pull your position outside as your K. Okay? Direction Z multiply X, you can pull it outside as well. Okay? So you will have another new vector we call the vector of position. And we will use an equation if you have some notation and multi-dot notation, and this one equals to a scalar. This is from single vector identity. You use this equation, then you can change your X, Y, Z direction E into this new form. Okay, this is only positive N direction. The wave to the positive N, then you can write down this one into, because you use this one multiply this one, and then your E0 has a component of directions. Okay. However, this is a way to describe the X, Y, Z, a new direction, and this is a more general plane wave solution other than just only X direction.
Okay.
Just expand this from our textbook. This is a cosine, this is a scalar, so you need to use a vector outside. Okay. And okay, next part, the polarization. What is polarization mean? In Chinese, polarization is 极化. If you have heard this before, right? Polarization, you have the direction. You have a direction. Something is not just that simple. Okay. If the wave discussed previously are called, okay, when the wave, the easy electric field, it is a linear polarization. In the words, linear polarization means I have the independent electric field in independent directions, but the phase of these directions are the same. The phase. If I have electric field, and I also have another electric field in y direction, I have two different electric fields, but they are in different direction. If they have the same phase, I will call that linear polarization. My phase is the same for this different electric field. Okay? When in your quiz, it's only one electric field, right? But I can have another electric field, put them together. Okay? If these two fields, their phase is different. If their phase are different, maybe it is not a linear polarization. If their phase is the same, this term is the same. Okay? They will have not linear, maybe circular polarization. We will call it orientation of electric field vectors. Okay, let's see something. Okay. This is an example of the linear polarization, because if these two electric field has the same magnitude, maybe 20 and 20, for this part, they are also the same. And for a linear polarization, cosine omega t minus k 0 z equals to cosine omega t minus k 0 z. Their phase are identical, meaning the same. Identical means the same. If their phase are the same, this is linear polarization. What is the result? If I put this E field together, I will have my resulting E field in this direction, right? I have y, x and the y component together. This is our E field. And if I am propagating in the z direction, so my y will be which direction? Anyone? Raise your hand. You can give me I can give you an extra point today. You want? Anyone? Show me your hands and tell me if you have the summarize. You add EY and the EZ together. Then what is the direction of Y? Anyone? Raise your hand.
It should.
Anyone want to answer? can come here and draw. Maybe use your hand to draw on the whiteboard. Tell us your answer. Where is your direction of H magnetic field? Anyone? Final H. Raise your hand. Anyone want to try? It's an easy question. Okay. Just use your finger and tell us what is your direction of H. 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 Okay. Draw on this board. Let's draw. Let me draw. If this is X and this is Y, where is H? Direction of H. Can you use 45 degree? H. What is H? Okay. Okay. Do anyone have different? Is that correct? Everyone agree? Yes. Okay, for this figure, where is the Z direction? Outside, right? Okay, so use your hand. If E field is here, the total E field, E cross H is your propagating direction, right? So it's a correct answer. Okay, and this is a linear polarization, right? What happens if the phases are different? Their phases are different. What happens? This is a linear polarization. Okay, let's just finish the mass calculation. Okay. So the resulting, the final, the combined E field is I have the direction of X and the direction of Y. This is why we need to write down this one, right? Because they are different. You have X component and the Y component. And there is an angle from the final electric field to X. And this angle is because they are the same. So arctangent 1 equals to pi over 4. Okay? If Z is 0, if you put your Z equals to 0, cosine 0 is 1, right? And then this is 1. And the resulting, if this direction is R, this is the something we talked about N and R before, right? We talked about the R, is the direction R. So you write down that this is the direction R, and this direction R and the magnitude is the square root of 2. Because it's 1 and the square root, and the direction becomes this direction. So you combine that to R direction. Okay, this is a linear polarization. We use this as an example of the generalized field. Actually, this is the second easy case, right? Okay, we have more. We talk about more. And the main part that we need to talk about it is because we want to talk about circular polarization, if the phase, they have the 90-degree difference between y, EY and the EX, if the phase is a little bit different. So there is something different. If the phase is different, the total E field is this part plus this part, and you can have you can write down the same thing here, but your phi, the angle is now different because of your phase is different. Okay, because one of the phase is cosine omega t minus pi over 2, another is omega t. You have the phase difference. So your tangent, arctangent become sine over cosine. You will become tangent, arctangent, tangent equals to omega t. So your angle is changing according to time. Your phi is changing according to time. So it will be like a circle. Your final vector, your final E field will be a circle because your phi is changing with t. Okay? Can you imagine what happened here? Okay, and this is a right hand circular. Okay, so let's see what happened here.
酥脆的能多益饼干，搭配鲜华润能多益榛果可可酱，吃出美味，全新分享。
So for the first part, it is a linear polarization. You have he used EZ and EY, these two directions. Both of them are the same, right? So your total E field is changing along the position and the time like a line. Okay, this is a linear polarization. Green one is EY plus EZ. Okay. So if they have a phase shift, if the phase of these two E field has a 90-degree difference, the total E field, see a green one, will look like, see? It will look like a circle. It's hard to imagine from the equation, but if you see this picture, you understand why we call this a circular polarization and why it's a linear polarization. So the difference is the phase, if they are the same or they are not the same. Okay? I think it's very easy to understand from this one, so every time I show this YouTube, it's much easier to understand, right?
Hey guys, I'm Kevin, and today I'd like to share with you some of my favorite experiments.
The more pointing vectors. Okay. Every time we talk about the E field and the H field, I will tell you that E field and H field, they are perpendicular in the perpendicular direction, and their way to propagating is in another propagation direction. We call that direction the direction of the pointing vector. This is a theory from the pointing. This is a pointing theory. it is a theory about the energy propagating. You propagate, your energy is moving. Your energy is moving. Let's see how much we talk about this one. Those are the derivations. Okay, let me simplify what I want to say. There will be electric field and electric field. Because you have electric field and you have also magnetic field, your energy stored inside the volume. Your energy restored is corresponding, electric energy restored is corresponding to your electric field. And your magnetic field is corresponding to your magnetic energy restored. Okay, those are the equations. And those are equations of the sinusoidal steady state case, and it is a time average stored electric field. It's an average electric field. The average stored energy. Because the energy will changing according to time position, right? It's changing, and it is the average. According to these two equations, we can have some result. Okay. I derived the equations in the textbook before, but I want to say this maybe easier, maybe in a more easier way. We try to do this. We do the divergence dot your electric field cross your magnetic field with conjugate. And this one is very similar to what we mentioned before. The average voltage in the AC current is 1/2 in the real part of VI conjugate. This is the average stored in the AC current, right? You guys remember it's AC power. Okay, so this form is, we have something like that, and we will take the 1/2 at the end. And those are very complex calculations. I did it by myself before, but I want to show that if you don't want to do the math for that, use the identity B8. You write down like this form, and then you separate your divergence into these two parts. Okay, according to this one, you separate this one into these two. So, which means your divergence vector E cross conjugate vector H equals to the curl E dot conjugate your vector H minus a very similar thing, this one. And then this is, I call part A, and then this is part B, and then they are more mass. Okay, for part A, because this one equals something, and then you put J equal to Js plus sigma E according to this reason. Therefore, your result will become like this part, this part A and the part B, whatever. Okay. Then you transfer your part A will equals to this, and we reorganize, and it becomes this part. And then we take an integration to the total volume, obtain this part, and use the divergence theory we applied before, and then we can obtain something. Okay. So, and multiply 1/2, and this is the final form. You got a relationship. First, for the first part, this is the power delivered by the source, the source power. Okay, so the source power, it has the part of Js and the electric field and the Ms and the H field. This part is talking about the power source. We call this the source power. Okay, equals to one part of that is, this is the most important thing. This is the pointing vector, the red part. The pointing vector. Okay, we talk about E cross H is P, right? Okay, so this is the pointing vector. And the S is maybe P or S. This is the pointing vector. We take a cross loop, the cross surface integration of pointing vector and multiply 1/2, and this will be PO. PO is the power flow out of the source, out of the surface. Your power from the source equals to your power transferred through to the surface plus this term. You have the sigma, and I think we have mu, and this is epsilon conjugate. This part is the power dissipation. It's a loss. This is a loss. I think this only talk about this term, and this term are the power stored, power restored. So you can see that your power from the source equals to your power transferred plus your power loss, because we have the sigma, this is a loss conductivity, right? Plus something, I know this is minus, but this is a plus this one minus this one, right? These two terms are related to the power restored. You understand? So this one is very, so you got the power restored. Oh, you have some part, you have an epsilon double prime, which is relevant to something, okay? Okay, whatever, let's go to the conclusion, and then we can take a break, okay? So this is the final form of our power transformation. Your power from the source, you can check your textbook. I think there are derivations, but this is the conclusion. Your power from the source equals to your power passed through the surface plus your power source plus 2j omega multiply your power, magnetic power restored minus the electric power restored. Okay, and those equations come from the derivation of this part. I think this is details. Yeah. This one won't show up in the midterm because I don't know how to ask you question. There are derivation, but I want to show you because this is important, especially this part. PO. Okay, if there is this lossless, you don't have this part, right? And we still have some energy restored. You have electric field and magnetic field. The source power and the PO is the most important, and the PO is this part. This is more important. and I want to introduce this vector we call pointing vector. The direction of the wave propagating. Okay? Can take the rest.
This part, and as I say, this one is very important. I will ask you maybe very similar question in the midterm, so you need to understand. So now we are, according to our quiz, most of you understand how to write down our electric field. And you know the Poynting series, right? So far, I assume most of you know how to write down it. And what is our next steps? First of all, we will have an electric field, and with its corresponding magnetic field. We have E and H together, and it's propagating in maybe P direction, or we call S direction. It's the direction of the pointing vector. Okay, this is the first part. Second, what happens if our electric field is moving and touch a boundary? This boundary means we have two different materials. So we will apply our boundary conditions in this part. If we have the electric field E, okay, maybe in the X direction, put down X, Y, Z. So Y is outside, and Z is this direction. Okay? This is my E field, and this is only the Z direction propagating to my surface. The surface is XY surface. So this is the direction of, maybe I use the same symbol, S propagation. Okay? And I have a Y, it is outside. Or maybe I write down like this is Y. This is H field. E cross H1. Okay? What is our E field? E is the same as I give you the question, the quiz. E0 exponential J, okay, omega t minus kz. And then the direction, it is X direction. This is direction of S. The key is that this is the direction of S. They are the same. Okay? And the direction of E is the direction of E. Okay? Everyone okay, right? So your K equals to, I use K0 equals to, everyone? Omega B omega C, right? Which is a square root omega multiply the square root of mu 0 epsilon 0. Okay? If this is air, if this material is air, okay, H equals to E0 divided by eta, and eta is the square root of mu 0 epsilon 0 equal to 377 omega, right? Multiply exponential, just copy that, j omega t minus k 0 z, and multiply by what? This is important, a different iteration. So your E field and the H field touch this boundary. And I tell you the boundary is air. Well, this part is air. Okay? What happened if I move to this part? What happened to this part? What is the E field and the H field for this part? If my wave is moving, I touched this boundary. I will call that this boundary is not air. I have epsilon equals to epsilon r multiply epsilon 0, and the mu equals to mu r multiply mu 0. This is some material. It's not air. Okay? This is its material. This field perpetuate, 穿透, perpetuate to this boundary. They will have two different field, two different pair of field. One of the part will perpetuate. Okay, let's rename E and H because I will have more than E and H. Okay. This is the incident, 入射, incident E field, incident H field. So I call it EI and HI. Okay. If I come here, they will have something go to another material inside another material. There are something be reflected back. Okay? Let's do something easier. For the first part, if my E field perpendicular to another material, we call the E field ER. What is ER? New question, right? This is old question from quiz. This is why I need to give you quiz. After quiz, you can have more additional information. If I perpetuate to here, I will have new ER and the new HR. The magnetic field is up. I'm sorry, wrong name. ET transmitted to another material. Okay, so ET equals to the magnitude will be changed, right? Because different material. So I call the new magnitude gamma multiply E0. This is like not 20 anymore. In the quiz it's 20, right? But if you are go to another material, you have a ratio. Just your magnitude will be only part of it. So we need to multiply some numbers between -1 and the +1. Between positive and -1. Okay, so this is a ratio. Okay, multiply your original magnitude E0 and okay, let me call someone to write it down. This is a quiz, okay? Finish it. Try to finish it. Because according to what I told you, what you so far you understand, which component should be changed, which should be not. Okay, Yan Boy, how about you? Do you want to try? No? Zhen Fang, do you want to try? Can continue. What's similar to that? Something similar to that. Okay, let me change. Okay, anyone who think which one will change? K, yeah, yes. So, okay, K will change to what will be K changed to? You cannot just read the book for me. Why? I didn't tell you what is here. Okay. First of all, you need to define what is this. Is this a lossless material or it is a lossy material, right? If it is also a lossless material, you will become another K. K can still write down like exponential J omega T minus K Z X. And your K equals to very similar omega square root mu epsilon. But in your textbook, okay, the part that I'm going to say is, if this is a lossy material, you use gamma equals to alpha plus j omega. So you use not only K, you use gamma, which is alpha minus j K or J beta. There's one more part of that. But they are the same thing. It depends on what the material is. It depends on the question. So if you want to know this one, you need to know first what is this material, and second, is that material lossy or lossless? Okay? If this is lossless case, you write down like this way. And if this is a lossy case, you use gamma epsilon E0 exponential J omega T and exponential gamma Z. Right? And sometimes you don't have this part if you don't think about T. And exponential is alpha plus or minus. Is that minus or not?
No. Yes.
要吗？它是 TA 加这个，对，它是阿法这个。
Gamma equals to alpha plus j k. And this is minus, right? This is negative. So I think maybe we need a minus, right?
还有一个这个，哦，不用，因为这
可是那个应该是那个前面的 是不是应该写 T 啊？还是
哪一个？
那个是写 T 还是写反射的那个？
这个是 T 啊。
那个是 T。
T transmit。
哦，我是说那个10前面那个。
哦。
那个应该是反射的。
I always think about. This is a ratio of the transmitting, the magnitude of yes. Those are another part. So this part is a ratio in perpetuate, and it depends on the. Okay. Let me check.
Yes.
From the minus.
Yes. Minus yes. Yes.
I write down this one because this is easy to understand. Okay, so if that is a lossy case, I use the gamma z, and in a textbook they don't put the t there. Okay, so here I use this part.
下面那个10也要乘，也是要 T。
So T E0 explanation minus gamma z. And, the same with the book. I don't write down omega t, but you guys know why, right? You can write down t or not, but in your textbook there is no t. No omega t.
No T.
And you use the same ratio, but this ratio is not eta 0. This is a ratio of the material. This is eta 0 because this is 377 for the air. But for this part, your ratio will be only eta, and your eta equal to the square root of mu r mu and epsilon. Okay, and then for your field, you have the same explanation by gamma z, and also. I think the most important thing is you need to remember this is the direction of x, and this is the direction of also the y. This is transmitted edge. Okay. You guys understand? Are you following? It looks like. Huh? No? You follow? Really? You have a material, your electric field, EI. You concentrate your EI, and then there is a ET. You write down ET like this form. T is the ratio between the magnitude here and the magnitude here. And there is a ratio between E field and H field for here. Okay. And there is another pair. If you have two media, two different materials, your EI will be reflected back. So there will be another ER, and the ER, actually for this one, you totally use the same notation we used before. Instead, your direction now is going to the minus z direction. You go to the positive z direction, right? This is a positive wave. But your refractive wave will go to another direction, so you need to use the positive here, the positive sign for a negative direction, or for a reverse direction. So this is important. This is one of the question, one of the mistake. Maybe you will happen in your return. You will write, you will forget this one. And the ratio is gamma. The direction is also x. And for this term, very similar thing. And the direction also the positive is. Because for the refractive wave, the direction is go to minus z. So you need to use the positive sign for this wave. And then you use your right hand. For this wave, you use x cross y equals to z, right? But for the refractive wave, your direction must go to your minus z, but you maintain your E field, the direction of E. So your direction of H is opposite side, the negative. E cross Y, E cross H, go to another S. This is your refractive wave. For a transmitted wave, it's totally the same, but your refractive wave is totally go to minus z direction. Okay? Are you okay with that? So you will have a minus z, but minus y direction, because your z is go to minus z direction. You okay? You guys need to see. Almost done here. And this is the midterm question. Except I will give you the numbers, the same as what we did, but I will give you more like a frequency will be changed because omega the same omega. Omega will not change that. But in here, you will have k, another k, or maybe gamma. It depends on the question is lossless or lossy case. If in here it is a lossless case, you just use another k. But for this case, if it is a lossy case, lossy material, use gamma here. Okay? Then we will finally obtain. And this is how we calculate the lossy medium. We talked about this before. This is a complete equations for incident wave, transmitted wave, and the reflected wave. 1, 2, 3, 4. Good for a midterm question, right? I just give you the question is like I give you the numbers the same as your quiz. I tell you it's from an air, and there is another material, epsilon r equals to something. Show me all the field, E and H field. You will see a midterm. And then you need to use this to give me the numbers for, I will ask you about what is the transmitted E field, what is the transmitted H field, reflected H field, and reflected E field. Okay? And, what else? What else? there is a equation that the electric field here is the same as electric field here. We try to use the boundary condition, right? What is the, do you remember the boundary condition of E? How about E and about D? What is the equation for the boundary condition E and D? On the boundary, the E field transient direction E field is the same, right? And the D is the same for the normal direction. Remember? Right? So this direction, the E field will be the same. We need to apply a boundary condition because we have a boundary. Therefore, from that you know 1 plus gamma equals to T. And for the H, you put a, for the H, you also have a boundary condition, right? And you got this another equation. Remind your boundary condition. Actually, this is not correct. This writing is not correct. It's like the transient E I and the transient ER equals to the transient, only the direction is the x direction. EIX plus ERX equals to ETX. Only one direction, right? Not the total. Okay? And H also have the same equation, like E, right? So EIX plus ERX equals to HT. And then if you put this number together, and I think put the Z equals to 0, so you don't have this part. At the boundary, Z equal to 0. Z equal to 0. So only the magnitude can make these two equations. You got these two more equations. And you get two equations, two unknown. If T and gamma, they are unknown. And eta and eta 0, they are already known because we already know the material. You can solve these two equations and obtain your reflection coefficient equals to eta minus eta 0 divided by eta plus eta 0. This is the same equation like for the circuit. Reflection coefficient equal to ZL minus Z0, ZL plus Z0. Remember this one? From the class? S11. Yes. Okay. Actually, you don't need to remember this one. It's the same like you have the impedance of the next material minus your impedance in your material divided by the impedance, the summation of these two impedance. So this the same equation, like your circuit. Okay? And for your T is this one. So, do you guys remember that? So, in your exam, for the question, I will ask you about what is reflected and incident wave. Please write it down. I will not give you T, I will not give you gamma. I will only tell you the there are two materials. You need to calculate the T and the inflation coefficient for me, and then give me the number, the value like you said. Okay, those are the value you need to calculate for me for the exam.